Hello. Today we're going to look at how are functions vertically stretched and compressed. Well, so far we've been looking at A, H, and K, right? What do we know about each of these? Well, so far we should know that H shifts the graph left and right, the K shifts the graph up and down, and if A is negative, the graph is reflected over the x-axis. Well, to vertically stretch and compress, we have to look at A a little harder. If A is greater than 1, we have a vertical stretch. For example, check out these graphs down here. We have the parent function f of x equals the absolute value of x, whereas this function is 3 times the absolute value of x. So it looks like someone grabbed it from the top and bottom and pulled and stretched it, and that's why we call it a vertical stretch. Now, if A is between 0 and 1, we have a vertical compression. So we can see that here. Here's our parent function, and then this one looks like it got squashed down from the top, right? Because this is 1/5, so between 0 and 1. So we don't say below 0 because if it's negative, all the negative does is flip a graph over the x-axis. All right, so let's practice these, but let's keep one more thing in mind. Stretches and compressions affect the y values. Okay, those are our dependent values. The independents will just stay the same. So let's look at f of x equals 3 times the square root of x. The parent function is the square root. So I'm going to go ahead and plot the square root main points, 0, 0, 1, 1, 4, 2. Okay, now the transformation is that it's been vertically stretched by a factor of 3. So why do we say by a factor of 3? Well, a factor indicates multiplication, and it's because you're going to multiply each of these y values by 3. To help us see what's happening, let's look at a table of the values. All right, so we started off with 3 x values, 0, 1, and 4. And then the square root of x, those were those y values because f of x equals, the square root of x for a parent function. So square root of 0 is 0, 1, 2. And then to find our new stretch, we're just going to take our parent function and multiply them by 3. So this would be 0, 3, and 6. Okay, so all I did was I took the y values and multiplied them by 3. And see on the graph here, 0, 0 will stay the same. This gets stretched, so 1 gets multiplied by 3 to 3. And the y value of 2 is multiplied to 6. And now this the square root function has been vertically stretched. Looks like someone pulled it from the top. So let's try it with this function here. f of x equals 2 times x minus 1 squared. The parent is a quadratic, and its transformation, it's got a vertical stretch by a factor of 2, and it's been moved right 1. So let's start by plotting our parent function, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. All right, so each of these y values has been multiplied by 2 and then is shifted right 1. So here this 4 becomes an 8 and then shift it right 1. The 1 gets multiplied by 2, so 2, and then shift right 1. Um, 0 multiplied by 2 is 0, shift right 1. And then so on and so forth. We'll end up here by multiplying these all by 2 and then shifting right 1. And so now we have a skinnier quadratic function because it's going to grow faster. That's what the A does. It makes it grow faster or slower. Right, so let's try this one last time. We have f of x equals negative 1/2 of the absolute value of x plus 2 minus 3. So the parent function is an absolute value. Let's go ahead and plot out those points. So again, we need to have these points memorized. Now, each of the y values is not only going to be multiplied by 1/2, but it will be a negative 1/2. So the transformation should be that it's reflected over the x-axis, that's what the negative does, and then it'll be a vertical compression by a factor of 1/2. In a case like this where we have so many different transformations, it's okay to plot the points a lot of times. So go ahead and start by just multiplying each of these y values, like 2 right here, by negative 1/2. 2 times negative 1/2 is negative 1. And plot that point. 1 times negative 1/2 is negative 1/2. 0, 0, right here. So now we've taken care of this negative 1/2. Now all we have to do is shift these things left 2 and down 3. So each point goes left 2, down 3. So I just took this point, left 2, down 3. Left 2, down 3. The shape should remain the same now that we've already compressed it. And here we have our transform function. And that's how we stretch and compress our parent functions. Goodbye.